We present DayDreamer, World Models for Physical Robot Learning, a new tool which enables researchers to train policies from scratch directly in the real world with high sample efficiency. Traditionally, training robots that work in the real world requires leveraging large amounts of simulation data under domain randomization, or arrays of robots working around the clock to solve tasks, amounting to hundreds of hours in training time. An alternative approach is to use learned world models, which learn to predict the environment and enable policies to be trained within the learned world model. Such an approach has many benefits, including data efficiency, data generation via imagined rollouts, online planning in the learned world model, reusing the world model to solve other tasks with no additional data, offline learning, and better exploration techniques. DayDreamer applies learned world models to real-world settings. First, an agent interacts with the real world and adds its experience to the replay buffer. This experience is then used to update the learned world model, and the actor critic is trained to maximize return within the world model. In this work, we learn policies for 4 different robots without the aid of simulators. In the first experiment, an A1 quadrupedal robot learns to walk from scratch in 1 hour. We also learn visual pick-and-place policies from sparse rewards. Using the same hyperparameters across all experiments, we achieve good performance. We open-source the project code to allow other researchers to perform data-efficient robot learning in the real world. DayDreamer interacts with the environment by observing inputs and producing actions. Observations are encoded into latent states, and subsequent latent states are fused into a single hidden state, automatically performing sensor fusion and removing the need for manual state estimation. The hidden states are decoded into the original observation, and the reconstruction loss is used to update the learned world model. During training, the actor is seeded with an initial state from the replay buffer, which is encoded into a latent state that is later fed into a policy. The policy produces an action, which is applied to produce an imagined state transition. The agent also receives rewards throughout this process, which are used to train the actor critic. When applied to the A1 quadruped, DayDreamer learns a policy to walk forward in the real world in under 1 hour. The policy receives joint angles and IMU estimates as an input to the policy and outputs target joint angles. The agent is rewarded for remaining upright and walking forward while staying as close as possible to the nominal joint configuration. The resulting policy learns the following forward walking behavior. DayDreamer also continuously adapts to external perturbations, such as pushing, in under 10 minutes. We also learn visual pick-and-place policies on the UR5 robotic arm using sparse rewards. Here, the policy receives raw RGB images and pixel observations as inputs, and outputs the desired end effector movement in Cartesian space. The agent is given a small reward for grasping an object and a large reward for moving the object from one bin to another. We apply the same technique to the X-arm, a low-cost manipulator. We also apply DayDreamer to a vision-based navigation task. The goal is to drive the wheeled robot from an arbitrary start position to the square goal. The policy input consists of raw RGB images, and the actions consist of individual wheel torques. DayDreamer establishes a strong baseline for future physical robot learning experiments, and we'll be open sourcing the code for people to build on.
Oh, he's leaving. He's leaving.